All right, we are going to get into the calculations involving the titration of a weak base with a strong acid. Make sure you've seen the video that I posted right before this, just so you have some background on the calculations we're going to be doing. I also went ahead on the screen and just worked out the reaction between the weak base, which is triethylamine, and hydrochloric acid, HCl. The weak base is going to accept the proton from HCl to form its conjugate, which we're going to be using in various calculations, and then the chloride ion. I also went ahead and used the volume and molarity of the weak base along with the molarity of the strong acid that's going to be used in order to find the equivalence point. So at 20 milliliters, I'm going to know that I'm at my equivalence point, and that also tells me that once I've added 10 milliliters of hydrochloric acid, I'm at my half equivalence point. So both of those are going to become important pieces of information later on. All right, so let's get into the first calculation, and this is just before any HCl has been added. So all we're doing is finding the pH of a weak base. So our weak base, which is that triethylamine, is going to be reacting with water here. Okay, remember, it's going to act as a base, so it's going to accept a proton from water. So you're going to have CH3CH2. And then NH+, be careful with your charges, and then that is going to form your hydroxide ions. And it's that concentration of hydroxide which will then get us to our pH. All right, setting up an ice table here. Our initial concentration is 0.1 minus X. And going ahead, we're saying there's 0. Another one there, and then we're going to assume that the autoionization of water is less than 5%, which it is. All right, now we will end up actually needing to use the quadratic here. We're going to skip that part and just keep it pretty simple, but that is something that you would need to do just because it does end up being greater than 5% when we go to simplify this one. But for our purposes, we're going to skip that. So we're going to use our KB that was given to us. So 5.2 times 10 to the negative 4. That is going to be equal to x times x, or x squared, over that 0.1. And again, I'm going to simplify it. I will tell you right now when we go to find it, we're going to get 7.2%, which is not less than 5%. But again, you could go ahead and use the quadratic for those of you that want to do that. All right, if we go and we solve for x here, and keeping in mind that x is equal to the concentration of hydroxide, okay, you're going to find that your concentration of hydroxide is 7.211 times 10 to the negative 3. Okay, from there, you would go and find your concentration of hydronium, okay, using the kW, and then from there, taking the negative log of your hydronium, you're going to get your pH value, which you would have as 11.8580, just keeping with the 4 sig figs. So that would be your calculation of the initial weak base, which makes sense. It should be greater than 7. All right, at point B, it says after the addition of 10 milliliters of your 0.1 molar HCl. So this is at your half equivalence point. Okay, so we know that we are going to determine the pH, or we can just based off of the pKa. So we have the Kb right now, so we can use the Ka, or get the Ka taking the Kw and dividing by the Kb that was given to us. And when you plug that in, you get 1.9 times 10 to the negative 11. So then from there, we can take the negative log of that, so our pKa, which would be the negative log of 1.9 times 10 to the negative 11. That ends up equaling 10.72. And then because it's at the half equivalence point, our pH is equal to the pKa. So that would also be equal to our pH. All right, so that would be the half equivalence point. Again, it's just an extra step because of the fact that we're working with our Kb. So we have to find Ka first. So one extra step compared to the weak acid with a strong base titration. All right, as we keep moving along, here we have 15 milliliters of a 0.1 molar HCl that's been added at that point in the titration. So with this point, we're before the equivalence point, so we're going to have a buffer calculation, so we can use our Henderson-Hasselbalch equation. So in this one, I'm going to do a little bit different just to, I can save a little bit of time, but also show you how you could simplify this, is I still need to know the moles of my weak base that are present and the moles of HCl that I've added in. So for the weak base, which is CH3, CH2, 3. So I'm going to find moles of that. I had 0.02000 liters of it initially, so 1 liter, and the molarity was 0.1. So this would be 0.00200 mole. Okay, our HCl moles that was added, that's going to react with the weak base. I've added in 0.015. This is just the 15 milliliters, 00 liters. It happened to have the same molarity, so 0.1. And when you find that, you get 0.001500 mole here. So keep in mind that initial reaction that we had. So we had CH3, CH2. And just for time purposes, I'm going to simplify this a little bit. Now keep in mind that I'm going to have weak base still present. HCl is going to get completely consumed. I'm going to have some of the conjugate acid of the weak base produced, and while there will be chloride ions, that's not going to have any effect on my pH at all. So for this Henderson-Hasselbalch equation, pH is equal to the pKa plus the log of my concentration of my weak base. Oops. And then in the numerator, I have its conjugate. Oh, actually, sorry, I have to put the, remember this is going to act as the weak acid. So I actually have to put that in the bottom. That's one of those little trickier things that you have to keep in mind when you're doing the weak base. So you need to make sure that this is still the weak acid in the bottom, and then the weak base is going to be on the top. So CH3, CH2, N. Okay, so keeping that in mind, and that's why I always think it's pretty helpful to like just set that up for yourself, just like I did, so you can catch yourself earlier on. So how I'm going to set this up without using the table is I know my initial concentration, and I'm going to do this in moles, just to simplify. Again, we've talked about before how volumes end up canceling out. So even though ideally you would want to use concentrations, we're going to, and I should have put the brackets around these all the way through, we're going to use moles here. So my initial moles was 0.00200 mole. Okay, and then technically I had 0 mole of the conjugate before the reaction. When I added the HCl, the base was consumed, and it consumed or reacted with 0.0015000 mole. Okay, that amount of moles was then produced in terms of its conjugate, or the weak base that's present. So 0.0015000. Oh, and I think I'm adding in an extra 0 here. On there. So that's just kind of going back to our buffer calculations because that's what we're doing. I just simplified it a little bit without showing you the full ice table. So then when you go ahead and you plug that all in, you should get, keeping to the 4 sig figs, 10.2429. Okay, and again, this is before your equivalence point. It's in the buffer region. So you can rely on that Henderson-Hasselbalch equation. If you need the full ice table, like we did with the weak acid strong base, go ahead and do that. I just kind of threw it all into the equation to start. All right, question D, it says after the addition of 20 milliliters of your 0.1 molar HCl, this is at your equivalence point. So this is where we're going to have the hydrolysis of a salt. All right, so this is where we have our 2 ice tables. The first one is going to be the reaction. So I'm going to write that out again. And I'm just going to leave out phases just for simplicity here. Okay, so you're going to be producing your conjugate of your weak base, which is going to become very important in this step. And then your chloride ion, which is really just think of it as like a spectator ion. Nothing's going to really occur with it, we're not concerned with it. So when we look at our ice table for this, we already know that we had 0.002000 moles. And if it's at our equivalence point, we also know that it has to be how many moles are present for HCl. Okay, and then we have 0. All right, so then on this part, they're gonna react together, and the 0.002000 mole is gonna get consumed, but that's going to then produce 0.002000 mole of the conjugate. And this is the part where you have to remember to divide by the total volume. So the weak basis was 20 milliliters. And so was the weak acid, or the strong acid. So when you find that concentration, it is going to be 0.0500 molar. And again, that's equal to the concentration of the CH3, CH2, and H+. Okay, that is going to be treated as your salt, and this is going to undergo the hydrolysis part. So then we are going to take that conjugate, which is going to act as a weak acid. So we have CH3, CH2, and H+. That is now going to be reacting with water. It's acting as an acid here, so it's going to donate a proton so that it reforms the weak base. And produces hydronium, which we would expect because we should be producing an acidic salt here from our reaction. So then going through our next ice table to set this up, we had 0.0500 molar, 0 there, and then we're going to say 0 for our weak acid and hydronium. And then proceeding forward like we've been doing, minus X, X, and X here. So we're going to do this to figure out our concentration of hydronium. Now, we're working with this as a weak acid. It's producing hydronium. So we need to do this calculation in terms of Ka, which again, you could find with your Kw divided by the given Kb. We already found that on the previous page, so it was 1.9 times 10 to the negative 11. This would be equal to X squared. And we're going to simplify it down, get rid of the minus X here. When we do that, X, in this case, based on our equation, is going to be equal to the concentration of hydronium. And then for this one, let's check my answer here so I keep consistent with the sig figs. You would end up getting 9.7468 as my pH. Oh, sorry, that's hydronium. And then if you take the negative log of that, so sorry, that should be times 10 to the negative 7, your pH at that point would then be equal to 6.0111. And that would be your actual final answer, which matches up with the fact that it should be less than 7. Okay, so obviously when you're at that equivalence point, it's going to be a little bit of work, just like in the last one, with a weak acid, strong base, with a weak base, strong acid. You have to show, first off, your reaction that produces your conjugate of the weak base, which is then going to undergo your hydrolysis, which will then give you your pH. And then E is just like what we did in the last one, so we only have a few seconds left. So you would, in this case, see that you have 5 milliliters of HCl in excess here. Okay, you would do that to find your moles, which you would use your stoichiometry here, or dimensional analysis, I should say, to get that. You have 5 times 10 to the negative 4 mole. Make sure you divide by that total volume here. So 0.02, sorry, I'm not putting in sig figs. I'm just trying to get this part done so you can see it. Total volume, that would give you the concentration of hydronium. and then your final pH, and you can check this, and for some reason I have it written down in 3 sig figs. I have no idea why right now. You should get this as your final answer.